presentation that I will discuss in today's session. 80386 signals we'll discuss, and then bus cycles also will cover, right? So it may take 2 or 3 sessions to cover all these topics, right? Now, basically, this is one 32 pin grid array package that of our microprocessor, right? We call it as a PGA, right? Pin grid array. There are several packages which you may come across in future, and we have already discussed about the DIP packaging and all. So this is one of the packaging of ICs, right? So this is basically PGA, pin grid array. So if MCQ based questions are there, then mainly like PGA may be asked for long form, right? So, and then how many pins are there, right? So physically 132 pins are there, right? So whatever the pins which we can see on this particular chip, right? So here basically all these chips are basically the pins which are coming out from the silicon wafer are basically connected to the motherboard through the socket, right? So processor socket will be there, and then you can see the pin numbers are given here, right? So here you can see A to P is there, then 1 to 14 is there, so like that. And this type of packaging, it is known as pin grid array, right? So this diagram is it will not be asked in the examination, right? So don't worry about it. So we will talk about the next part, right? Now, before we actually start discussion on various pins and pin functions, right? Let me highlight about the symbols which are basically used in upcoming discussion, right? So hash is the term or the character, special character which is used to indicate that given signal is active low. Given signal is active low, right? So we have already seen in digital electronics, right? So the variable a is basically can have high value and low value. So if it is low, then we used to denote it as a dash, right? So a hash is alternate way to represent the same condition. So the signals which are active low, right, will be indicated with the hash sign, right? In the data sheet which you have with of 80386DX, then that hash sign is used, right? So here you can see this hash sign will indicate that if it is an input signal, then to to get that particular or to activate that particular activity related to that pin, it requires low signal on that. If it is output signal, then the signal is known as active whenever that particular pin is low, or other. If it is high, then it is treated as an inactive signal. So here hash sign indicates that the given signal is active when it is having low signal. Then I is the other symbol, right? This indicates that this pin is input signal. O is there, which indicates that this pin is output signal. I oblique O is there, right? That indicates that on the same pin we can have input as well as output signal. And then dash sign is there, so that indicates that no electrical connection is there, right? So these are the symbols which are basically used in our discussion. In my next slide, we will discuss about the functional pin diagram, right? This is known as functional signal groups or functional pin diagram. In our syllabus, it is mentioned as functional pin diagram. Here you can see total 85 pins are there, right? Which are basically defined in your pin diagram. And whatever the pins which we have seen in on the chip, right? 132 pins are there. Basically, there are several NC pins are there, and other are basically power signals are also there. Getting this? So here you can see total 85 pins are there. All right. Now, if you see, it is divided in different functional groups. Now, everyone should remember about these all functional groups, because there are several operations, right, in which we need these signals, right. In this unit we will be talking about the bus cycle. So in bus cycle, as it is associated to the external interface, and to perform or to connect your external devices to your processor, we need these pins. All right. So there are several functional groups which are there. The first of, we'll start from the right side. On the right side, you can see 32-bit address bus is there, right. The first group that indicates is 32-bit address bus. Now this we have discussed in short earlier, right. Now I will elaborate more about it here in this case. Now when we are talking about 32-bit address bus, it is from A0 through A31, right. So total A0 through A31. Now, as we discussed in a bus interface unit, after the address translation, right, it is going to encode your lower 2 bits in the form of byte enabled signals. And those byte enabled signals are BE0 bar through BE3 bar. So BE0 bar, BE1 bar, BE2 bar, BE3 bar. These are the byte enabled signals. So lower 2 bits are encoded in the byte enabled signals form, and the remaining 30 pins are sent as it is. So A2 through A31 pins are made available for the external interface, along with this encoded lower 2 bits. So total 34 pins are taken out, but ultimately it is going to form our 32-bit address bus. Now, why these byte enabled signals are, right? So let me access the, okay, so here, okay, I will use the Jamboard here. So start new whiteboard. All right. Those who joined late, mark yourself present in chat box. Is the Jamboard accessible to everyone? Visible to everyone? Is this visible?
Yes, sir.
All right. So let me select the pen, right? Now, here if you see, as I am talking about the pen we'll use now. See, I told you that we have A0 through A31 pins are there. These are basically the pins which are created by your address physical, the memory management unit, right? So that segment translation and page translation. After that, we get these 32 pins. Bro, out of these, lower 2 bits are A1 and A0. I will write in this format, right? A1 and A0. Now, these 2 pins, we have 4 combinations, right, with these 2 pins. So 0 0, right, then 0 1, then 1 0, and 1 1. This is very interesting point that I'm talking about, right. Now once you have this lower 2 pins, right, as A0 and A1, right, your encoding mechanism, it convert it into byte enabled signals. So encoding happens in the bus interface unit, and those byte enabled signals are basically enabled, or those are activated. So those are basically, if you see the pin names, those are BE0 bar, BE1 bar, BE2 bar, BE3 bar, right. These are the byte enabled signals, right. Now Why 4 byte enable signals are there? Because we have 32 bits data bus, right? 32 bit data bus. So we have data bus D0 through D31, right? So how many bytes are there? So we have 4 bytes, around 4 bytes. Now these 4 bytes may not be used in all bus operations. May not be used means what? Depending on the operand size, the number of bits will be involved in current data transfer. So during the data transfer, what other bits or other data lines are expected to do? Those are to be there in the tri-state conditions. There should not be any technical, the electric signal should transmit during that particular operation. So it should be in the tri-state condition. All right. So to make the respective set of 8 bits enabled, we are your processor uses this byte enable signal, and there is a direct association of this byte enable signal and the data lines, right? So what that association is, so I will elaborate here. Those are for to enable D0 through D7. D0 through D7 will be your processor will be enabling BE0 bar, right? So I can write here bar because I have marker. So it is BE0 hash sign. Then we have next data lines, next set of 8 data lines, D8 through D15. And for this we use BE1 bar, right? Then we have D16 through D23, and the associated byte signal is BE2 bar. So parallelly you can note down in your notebook. This is very interesting point, right? And in many literature you will find the same explanation, but whatever the next point that is there, that you need to read the actual manual. So you make keep yourself in line to the discussion, right? Next is D24 through D31. All right. So and for the associated byte signal is BE3 bar, right? In Jamboard it is quite difficult to write using this mouse. So all right. So this is the association of your bytes enable signals and the respective data byte. Respective data byte. Now, whenever it is expected to transfer a byte from given data lines, then your processor is going to make the respective byte enable signal low, indicating that for the current data transfer, these data lines will be used. Right now, see, one byte enable signal is associated to one byte, means associated to 8 data lines. What is that relation? One byte enable signal is associated to 8 data lines, right? Now, what if the operand is 16 bit? What if operand is 16 bit? So how many byte enable signals are expected to enable? Can anyone give answer? For one byte enable signal is associated to 8 data lines. To transfer 16-bit data, how many byte enable signals are expected to enable? Can anyone give answer? This is a very simple relation. And try to give your answer immediately. How many byte enable signals are required to transfer 16-bit data? अरे प्रश्न कळाला नाही का तुम्हाला लोकांना? So every time I should not select the student and I should ask, right? Everyone should give attendance and at least one student should unmute and give the answer.
Sir, 2 weeks.
Pardon? Yes, Shreya.
Sir, 2 weeks. Is it right?
2 byte enabled signals,
Sir, 2 weeks.
right? 2 byte enabled signals are required to transfer 16-bit data, because I told you to transfer 1 byte or 8-bit data, I need 1 byte enabled signals, right? Now, when we when you explore more about interfacing part, right, interfacing memory with your processor. So on next Jamboard, I will draw that particular diagram because it is out of scope of our syllabus, but still for your understanding, my drawing is quite, I'm from childhood I am the best artist, so you can understand my drawing, right? So here if you see, these are the memory locations, right? This is how our memory chip is seen from a processor side, right? This is how the memory chip is seen from processor side. And here our data bus, which is 32-bit data bus, this is our 32-bit data bus, right? And the lower data lines are connected to this bank, right? This is basically, we can call it as a bank. So here you can see these are the bidirectional lines which we used to show, right? And the lines associated to it is a D0 through D8. D7 it is, all right, D0 through D7. And like that, you can see the bidirectional lines are here, right? And this is your D24 through D31, right? And this is complete 32 data bus. This is how your physical interfacing is done, right? With the memory bank, right? So we treat it as this is as a complete memory bank, right? So it may include ROM, RAM, so whatever the different memory chips we have, right? Now, as we have discussed in earlier Jamboard here, BE0 bar, whenever BE0 bar is enabled, then any a byte from the selected column of this particular memory bank, right? Here you can see this is basically the selection, right? Any of the byte will be transferred, but which byte, then that depends on the remaining 30 address lines. So how it is going to decide which byte is to be transferred? Now, if I write a physical address here, and if I write the physical address, now here you can see what is the byte address, or what is the address of this particular memory location here. If you see the byte address of this location, as this is the first byte in my memory bank, so its address is 0000. 32-bit address I will write 0000, right? 8 bits are there, and I will put H here to indicate that this is a hex number, right? So it is 0000, then 0000. This is our 32-bit address of this particular byte, right? Now, here if you see, what is the address of this location then? This location. Can anyone tell what is the address of next byte after the first byte? What is the address? I'm expecting answers. What is the address of next byte after 0? What is the address? Do you want me to just stick to the syllabus and I should continue with my discussion with the pin functions? Because this is of no use if you don't focus and don't interact with me, right? So ultimately you are wasting my time and my energy. After the address 0, what is the next address? Next byte address? Yes, please. 0 नंतर काय तर तुम्ही लहानपणापासून शिकलेला आहात ना. What is the next address after 0? Yes, Veer is there. Yes, Veer, am I audible? Yes. Okay, so I will simply close it. Where is the PPT? Okay, I will stick to the syllabus. All right, so don't worry. See, the 32-bit address lines are there, and byte enabled signals BE0 bar through BE3 bar is there. And as I told you, BE0 bar will be enabling the lower byte. BE1 bar will be enabling the next byte. BE2 bar will enabling the third byte, and BE3 bar will be enabling fourth byte. Right, and depending on the operand size, it will decide which how many byte enabled signals are to be enabled, right? So now if the address is 0, that means the lower 2 bits are 0 0 in my address line, and in that case BE0 bar will be by default, it will be low. BE0 bar will be by default, it will be low. But if the operand required to transfer in current bus cycle is 2 byte, that means 16 bit, in that case I need 2 byte enabled signals. So in that case BE0 bar, as I told you, BE0 bar is mandatory, it will be low whenever the address is, well, lower 2 bits are 0 0. So along with BE0 bar, right, BE1 bar will also low. Bro, if the data transfer requirement is say 32 bit, so 32 bit, for 32 bit we need 4 byte enabled signals. And as I told you, if the address is 0 0, lower 2 bits are 0 0, then BE0 bar will be low. In addition to that, all these 4 byte enabled signals will be low. So depending on the operand size, your processor will decide how many byte enabled signals are to be made low, right? Then we will talk about the bus cycle definition. In bus cycle definition, these pins are very interesting pins. These pins are going to decide what operation will be carried out or what operation is initiated by the processor. Right, so bus cycle definition. So in detail we will discuss about this. There is a separate chart, but at this stage we can easily highlight about these signals. W oblique R bar, W oblique R bar, D oblique C bar. W oblique R bar indicates whether it is a write cycle or read cycle. So depending on the instruction which is in execution, it will decide whether it is a read cycle or write cycle. Then D oblique C bar, right? This will decide whether it is a data transfer cycle or it is a control cycle, right? Then M oblique IO bar is there. This M oblique IO bar will decide whether the current bus cycle is a memory related to memory operation or IO operation. And the log bar is the signal. This selects the given bus cycle is logged one. And this log signal is very interesting, that we will discuss in chat, right? Then PEREQ, then busy bar and error bar. These three signals are associated to coprocessor signaling. Right. So whenever we are connecting coprocessor, as we know, with the 80386, we have a coprocessor 80387, and whenever we connect this coprocessor, right, to interface the coprocessor with the main processor, this 80386 will be the main processor. So there will be these three signals which will be synchronizing the communication between your primary processor, which is your 386, and the core processor, right? The next one is the power connection. So VCC and ground connections will be there. Then there are three hardware interrupt pins are indicated here, right? So these are reset is there. So reset signal will be resetting the complete microprocessor, and it will start from the reset address. Then NMI is there, which is a non-maskable. Name itself indicates that it is a non-maskable interrupt. Then next one is the INTR. So this is the interrupt request pin, right? This is a maskable interrupt. NMI is non-maskable, but INTR is maskable. And there is a relation between interrupt enable flag, IF flag, that we have seen in flag register, right? So that IF flag will decide whether the interrupt received on INTR will be serviced or not, right? So we can enable or disable this INTR interrupt based on the requirement of our software, right? Then bus arbitration is the another set of signals. Bus arbitration in multi-processor system, right, where multiple processors are connected. In that case, to hand over or to share the common resources like the bus, common system bus, right? Now on this common system bus, at a time one bus master can transfer the data. So to synchronize that particular operations, we have this bus arbitration signals, hold and HLDA. So hold will be the input signal which indicates that there is a request for bus, and HLD indicates that the hold is acknowledged. So whatever the request that was sent by other bus master, permission is given to the other bus master to transfer the data. Then bus control signals are there. Here bus control signals are ready bar signal, ES16 bar, NA bar, ADS bar. In detail we will discuss in a table. So bus control, these signals are going to control the operation of data transfer or whatever the bus operations. Then 32 pins are there per data bus. So here this 32-bit data bus is actually used to perform the data transmission operation, right? And as I told you, depending on the number of operand size, the number of data lines will be used, right? So for 1 byte operand, any of the 4 byte out of D0 through D31 will be used. And as I told you, that will be decided based on the address, right? And the address association, I told you, if the lower 2 bits are 00, then BE0 bar will be enabled, right? So at least that BE0 bar will be enabled, right? If the address is 01, lower 2 bits are 01, then BE1 bar will be used, right? So if the address is 10, lower 2 bits are 010, in that case BE2 bar will be enabled. And if the lower 2 bits are 11, in that case BE3 bar will be enabled. And depending on the byte enable which is enabled, right, the respective data lines will be used for the current data transmission, and other data lines will be in tri-state conditions, right? So high impedance state it will be, and there will not be any electric value on that. It will not be 0, it will not be 1, it will be logically disconnected, right? Then CLK2 is there, right? So clock 2, here we apply the frequency, right, the external frequency, and depending on the processor clock, right, the requirement of processor clock, it will be multiplied by 2, so 2x clock. So that's why it is called as CLK2, right? So whatever the clock requirement is there, twice of that external frequency will be connected here, right? So this is the detailed explanation of pin functions. As I told you, CLK2 is basically type is given in this table, so that is input. CLK2 provides the fundamental timing for your 80386. right? Then data lines I told you D0 through D31. It is a data bus and it is a bidirectional bus, right? So we can have input and output operation on the same lines. So using these data lines, we can transfer data from memory, I/O, and interrupt acknowledgement read cycles, outputs data during memory read and I/O write cycles. So for no, all type of data transmission, we use these data lines. Then out of address lines, 32 address lines, A2 through A31 are listed separately, which are output. And these are actual physical memory addresses or the port address, right? So port IO addresses. Then byte enabled signals are there. These are in the, as I told you, these are going to indicate which byte of data bus or which bytes of data bus will be taking part in current data transfer or current bus cycle. Bro, then W oblique R bar is there. So W indicates write, R indicates read. So if the current bus cycle is, say, for example, memory read, in that case, this pin will be low because we are performing read operation. If the current bus cycle is memory write, in that case, this pin will be high, indicating that it is a write operation, right? So this is one of the interesting pin in which defines the type of your bus cycle. Bro. Then D oblique C bar is there, data oblique control. And this particular pin will define whether it is a data bus cycle or control bus cycle. So there are several types of bus cycles which will be initiated by your processor. So here, this particular pin will define whether it is a data or control. So in a bus cycle definition pin that distinguishes data cycles. So data cycles are either memory or IO from control cycles, right? So data cycles are associated to memory or IO operations, and control cycles are basically interrupt acknowledgement, halt, and the instruction fetching. These are considered as a control cycles. So whenever there is control cycle to be initiated by processor, then this D oblique C bar will go low, right? And whenever data cycle is to be initiated, in that case, this will become high. D oblique C bar will become high, right? Then M oblique IO bar is there. Now this is very interesting one, M oblique IO bar. Now whenever we want to perform the memory operation, in that case, this M oblique IO bar will be high, indicating that the bus cycle which is initiated by your processor is a memory read or write cycle, right? And this is the pin which will differentiate the bus cycle, the memory bus cycle from the IO input-output bus cycle. Now, the interesting point that I want to highlight here, when in the last session, the concluding statements I highlighted about the memory organization and IO organization, right? So you can make note of it because this is very interesting point that everyone should remember and everyone should know, right? While performing memory operation, your processor generates 32-bit address. Right, so 32-bit address will be physical address that will be generated by your processor, right? So with respect to these 32-bit address lines, we can connect 4 GB of memory, 4 GB of memory. So any of the byte from 4 GB we can access, right? Then when it comes to the IO operation, for IO operation, you can note down, for IO operation, it generates 16-bit address. Maximum of 16-bit address, right? So maximum of 16-bit address will be generated, and in that case, we can connect up to 64K kilobyte IO devices. 64K IO devices, and when we actually it is not there in our syllabus, but it is in terms of bytes. So if any device IO device which is of 16-bit, in that case it will occupy 2 IO addresses. It will occupy 2 IO addresses. So if all devices are 16-bit, in that case 32K, sorry, not 32K, 32K word size IO devices we can connect. Byte size IO devices, if I treat that all devices are byte size devices, in that case 64K IO devices I can connect. All right, but if it is word size, that means 16-bit IO devices, in that case 32K IO devices we can connect. And if all devices are of 32-bit, all IO devices are of 32-bit, in that case 16K forward size IO devices we can connect. This is how the interfacing, IO interfacing can be done. All right. So this is very interesting one, right? So whenever we write the address space, so we used to always talk about the memory address space and the IO address space. So with reference to the given data, I told you about the memory address. So 32-bit address it will be, and for IO address it will be 16-bit. With reference to this, the memory address range will be from 0000 to FF. Right. So the address space is all zeros to all F. Right. But when we talk about IO address space, that is 64K, in that case the IO address space will be from 00. So I will just put it in the chat box so that you will understand. See the memory address range. Memory address range will be 00000000 H to FF H. Right, this is the memory address range. And what I told you about the IO address range. So for IO address range, your processor generates up to maximum lower 16 bits will be used in that case. So in that case, IO addresses that will be generated will be starting from 00000000 H to 0000 and then FF H. Now this is the IO address range. And based on this, you can see the same address range is there. So on the address lines, it will be having same values. But then how external devices will understand that this is a memory operation and this is the IO operation, that will be distinguished based on this particular pin, and that is M/IO. So whenever you are executing an instruction which is associated to memory operation, the instruction which is associated to memory operation, in that case your M/IO bar will become high. Right. So what type of memory operation instructions we can have? So I will just put it here, move, and then simple instruction move AL comma, and I will use the instruction saying ESI. So this is the instruction move AL comma in bracket ESI. What is happening here? We are reading data from the memory. Right. So my instruction move that I'm using is a memory related instruction. So ultimately it is going to make M/IO bar equals to high, and along with that it will generate the physical address, and that physical address will be within this range, right? So whatever the memory address range that I highlighted here. But when this IO address range will be used and when this M/IO bar will become low, whenever I am executing an instruction which is from the IO addressing, right? So IO addressing, so we can have out instruction, or we can have in instruction, right? So out and in both are instructions associated to the IO operations, right? And here in is basically read. So I'm reading it from where? So I'm reading it from the IO port, IO device. So in which what size of IO device is that? It will be decided based on the accumulator that I'm using here. Right. So move in AX comma, and then if I put the address here ATH. Now here in this case, the instruction that I have written is the direct IO. Direct IO means what? I have written this port address. ATH is not the value. ATH is not a number. Basically, it is not here. If I replace in with move, then what is the operation that will be carried out? It will moving AT into X. But with in instruction, it is not the value, immediate value. It is the address of a IO device. So 80H is the port address from where we are going to read 16-bit value, and that will be stored in AX. Right. So this 80H will be from this IO range, IO address range, right? From this IO address range, and during execution of this instruction, M/IO bar will become low, indicating that the address which is available on the address bus is for IO device and not for the memory device. So you can easily identify 80H is also a part of this particular address range, right? So memory address range. So 80H is already there in the memory address range, but to differentiate between the memory address range and the IO address range, we have this M/IO bar, and that will be made high and low based on the instruction that we are using. All right. So M/IO bar will be distinguishing between the memory cycle and the IO cycle, right? Then log bar is another pin. Log bar will be indicating that the given bus cycle that we have initiated is locked by the master. Right. Now, why it is required? Why that bus cycle is to be locked? Because during execution of this particular bus cycle, your bus master don't want that other bus master should request for the control of system bus. Right. So during this bus cycle, other bus masters will be kept on hold. Right. Their request will not be serviced unless and until this long bus cycle is over. Right. So this bus cycle definition, this is also bus cycle definition pin, and that indicates that other system bus masters are denied access. Denied access means what? Other bus masters will not get permission to access the system bus unless and until the current bus cycle is completed by your current bus master. Right. So that's why it is required to lock that particular bus cycle. Right. And depending on the requirement, this lock signal will be made low. Right. The bus cycles will be locked by your bus master. Then the next pin is ADS bar. Right. ADS bar is address status. Now, this ADS bar signal is basically indicating that valid bus cycle definition and address is available on the respective pins. Now, this is the very interesting pin. Whenever new bus cycle is initiated by your processor, ADS bar will become low, and for the remaining clock cycles it will be high. But also whenever new bus cycle is to be initiated, it is mandatory that ADS bar will become low, and along with ADS bar, your processor will place all the necessary signals on respective pins to indicate that the valid bus cycle is initiated by your processor. Right. So this is ADS bar interesting pin. So the valid bus cycle definition and address, that means, so in bracket the several lines are indicated, and these are W/R bar, D/C bar, M/IO bar, then all byte enabled signals and the address lines. So out of these you can see W/R bar, D/C bar, M/IO bar are the bus cycle definition pins, right? And BE0 bar through BE3 bar and A31 through A2 are the address pins, right? So the valid signals associated to current bus cycle will be available on these pins, right? And along with that, and this is happening along with the ADS bar. So here you can see this address status is one of the important pin, right? Then NA bar is there. NA bar is ultimately, NA bar indicates next address, right? Next address. And very interesting pin is this, right? This indicates that NA bar indicating that the address pipelining is requested. Address pipelining is requested means what? Your 80386 is having the special feature of address pipelining. Right, many of you may be knowing about the instruction pipelining. In instruction pipelining, what is happening? We are dividing our instruction execution in several parts, and then parallelly or one by one we can initiate the instructions. Right. here with the NA bar pin, with this address pipelining feature of your 80386, we can initiate multiple bus cycles. Multiple means 2 bus cycles, right? And how your external device will understand, or how your processor will understand that processor has to send or initiate the next bus cycle. So that will be indicated by NA bar. So NA bar is basically the input pin, right? NA bar is the input pin, and if this NA bar becomes low during the execution of current bus cycle, then processor understands that your external hardware, right? Let me clear about it. Your external hardware is capable of handling multiple bus cycles. Right. So if your external hardware is capable of handling multiple bus cycles, then and then NA bar will become low. Then and then NA bar will become low. And if NA bar becomes low, and if there is next bus cycle which is pending, then in that case 80386 initiate the next bus cycle. Right. So initiating the next bus cycles means what? Your ADS bar is expected to be low, right? So as I told you, in the first bus cycle already the ADS bar became low and the first bus cycle is initiated. But if it receives, right, during the execution of the current bus cycle, if it receives the NA bar low, indicating that the external hardware is capable of handling the multiple bus cycles, in that case your processor can initiate the next bus cycle before completion of current bus cycle. So this is overlapping, we call it as a pipeline. All right. So here you can see other pins are there, ready bar, BS16, hold, and so other pins we will see it in our next session, right? So I think here